Yeah, very good evening, and once again, welcome back to the session. And we are working with a data which is numeric, and so we have worked with y is equal to categorical data, and we have understood that under supervised learning algorithms, sorry, we need to go for either decision tree classifier or KNN classifier to understand the things in a better way. And we have got understand that we need to go through confusion matrix, and for any classification algorithms we can find these two. But now what is the stake when we want to go with y being numeric? Okay, what should we do if y is numeric? So supervised learning algorithm is divided into two. As I said, it is regression and it is a classification. We have seen classification models where the evaluation metric is confusion matrix. But when it comes to this regression model building can be opted when your y is numeric. Okay, so we are trying to find out the relationship between two events, and the relation was y is equal to f of x. So whenever we are interested with prediction for any unknown data, y is equal to f of x. So when we are trying to do a prediction with respect to unknown data, x is known to you but y is not known to you. And here the term y, the variable y, is called as dependent variable. Okay, it is called as dependent variable. This dependent variable can be predicted or can be understood only if x is given to you. X cannot be anything. X should be taken into consideration, which is really having a very, very good relationship with your y. So the point you should understand here is x is equal to f of x. This being, this can be anything, and this is your independent variable. Okay, this is our independent variable. Y is a dependent variable. If x is given to you, you can predict what is y. So this process is nothing but for any unknown data you want to predict a new value for unseen data, that is called as regression. So when you talk about simple linear regression, it is a concept of a straight line. Suppose I have, this is a basic equation, and I have to take into consideration a relationship between these two. This is my y, this is my x. So this is finding out via bivariate plots. It is done using bivariate plots. These bivariate plots are nothing but finding out the relationship between x and y. You can have multiple x, or you can have only single value of x for prediction of y. Right? So if at all I want to find out the relationship between these two, suppose given the budget for any ad and you have telecasting using a television, how are the sales happening? The budget allocated is 1 lakh. How much increase in the sales is happening if you're doing advertisement for one particular product? Right? 2 lakhs. What is the sales? Now, definitely this budget allocated and salary are related. Are they? Is a good point here. We should find out that. So to finding out that, we have a plot here to do that, which is called as a scatter plot. This is called as a scatter plot. Okay, in the scatter plot, you draw a line. Okay, you draw such a line. Okay, now this is my x. It is equal to 1 lakh, 2 lakh, 3 lakh, 4 lakh, 5 lakh. This is my money spent on ad to telecast it on television budget. Okay, these are your sales. 2 products, 3 products, 4 products, 5 products. If it is there in thousands, if the data is taken in thousands. Okay, now you got the line. Suppose now tomorrow when I want to spend 3.4 lakhs, that historic data is not available in my data I have collected. Historic data is we don't have any clue. We have for 1 year, 2 years, 4 years, but 3.4 it is not there. But 3.4 is not there. How do you predict it? For that reason, you draw a straight line and you try to find out the intersection between these 2 points. This is my TV budget. This is my sales of that particular product. If the advertisement is done via television or newspaper or Facebook or e-commerce, any portal or YouTube, whatever, different X's you can take and you will find out and you will intersect at this point, and this point you will find out and you will say that this could be the number of sales. This could be the number of sales. So what is going to happen here when this is the number of sales? Okay, but how can we say that this is the exact number? Just because you are having an intersection here, you are telling that this could be the sale. But suppose this is the original sale for me. The dot which I marked here is the original sale for me. So what is going to happen? This gap is nothing but we say that this is the original value, but this is your predicted value. This difference is called as error. This difference is called as error point. Okay, this difference is called as error point. This error is common for all the so many different data points coming up here. Right? You are predicting a value which is not known to you given your X, which is not the historic data. That is called as regression. Finding out the relationship between 2 models is called as correlation. Whether the whatever we have taken as a part for analysis here, is that really helping us to predict that TV budget is enough with the sales? We are trying to find out the relationship between both of them, and that correlation is what you find out. If that is a scatter plot would give you whether they are linearly related, whether they are having good relation with the direction or negative direction, and how important this is for prediction of your product sales. Sales of the product with an ad which is being telecasted on this. So this is going to help you to find out it is 0.85, 0.81, whatever it is. If it is greater than 0.85, then it is saying that yes, this is a very good input for prediction of your sales. If the relationship happens to be 0.4, less than 0.4, then it is called as worst model building. Called as worst model building. So this is our correlation. So for any data set, when you want to perform regression, the first thing is you need to find out the correlation, or you do a scatter plot. Right? You will check the dependency is there between both of them, how well this is important for prediction of Y. Once you get to know this, right, you are doing a scatter plot and you are trying to draw the line. trying to draw the line, in fact, it means that the line could not be always a straight line. The data got scattered like this. You are drawing the line, and that line is called as the best fit line, and that is nothing but we used to write in our school days, that is y is equal to mx plus c. It is y is equal to mx plus c. So relating this now, this is my intercept. Right? A line can be like this also. A line can be like this. A line can be anything of any shape. It could take anything like this. Okay, it can take anything, but you should get the best fit line. Should get the best fit line, and this best fit line is your target. To get the best fit line, you have a technique called as OLS technique, which is called as ordinary least squares technique. It is called as least square technique. So for each and every data point, right, you will get this. So these are the actual data points. But if your model has predicted this, so this you are mapping it, you are telling that and every data point, because your model will not exactly map the same value, same predicted value, and your actual whatever is given in the data, it's not taken into consideration here. So what is that your interest here? Your interest here is that you are trying to find out the best fit line and some of the square, okay, sorry. Some of the squared errors, these errors what you're getting, this is E1. Again, one more you have E2. Some of the squared errors should be least. This is called as OLS technique. Your line should give that. So why you are interested in that line? That line is nothing but using this concept of equation of a straight line in regression, y is equal to beta naught plus beta 1 x1, where beta naught is c, beta 1 is a slope with respect to the input what you have. That's what your y hat value. That's the one. So what are these beta naught and beta 1? Beta naught and beta 1 are called as estimates. They are called as parameters. Okay, they are also called as coefficients. Parameters which the model will give you, and you cannot touch them, you cannot compress them, you cannot tune them. Okay, so when you opt simple linear regression, if you have only one input variable and that being continuous and this is also continuous, you can go for simple linear regression. Okay, you can go for simple linear regression. But what if you have x being discrete? Right? You can go for dummy variable creation. You create dummies, convert them into numeric form, right? And then you have the data set. In fact, now if at all you have multiple variables, you have multiple variables like y, x1, x2, x3. Okay, that is nothing but you say that it is a multiple linear regression. Multiple linear regression. So that is all about the linear regression. So we are not bothered about our what we say, this beta naught, beta 1 value, how they are coming, and we are not interested to even by heart the statistical equation of R. Okay, this is small r. because that is nothing but your correlation coefficient, what I have explained. What your small r. Okay, this is something about your regression. So this is what I was explaining. Okay, so y is continuous, linear regression. If x is discrete, also apply dummy variables and make it into a simple linear regression model building. Okay, so now let us understand few important things when we are working with this data. Okay, let me show you the data set. So on daily basis, what we have to do? We have to import the pandas, import the numpy, import the seaborn, import matplotlib.pyplot as PLD. So you know that pandas is for data manipulation. You know that it is for numpy is for math. This is for plots. This is also for, this is for advanced plots. This is for plots. See here the data set here. The data set talks about four different, we have taken four different, but we can take one at a time and build a model. But the data set is having TV, radio, newspaper, and sales. Okay. So what is this TV, radio, newspaper, and sales? These are the different media platforms where you can do your ad campaign. Right? You can do it via radio, you can do it via newspaper, you can do it via television. If the product is being advertised via TV, the budget allocated is 230. If you take it, it is in lakhs or in thousands. Right? The number of product sales, it is 22.1. Or right, the sale is a continuous value here. So what we will do here is we will have to pick up whether this budget allocated or the budget input is it relevant for prediction of sales. Okay, so TV is good or radio is good or newspaper is good. Okay? Which one, if you do an ad campaign, which an ad is telecasted, you are getting more number of sales. Which one is giving you good amount of sales? So for that, what you should do, we should do EDA. If you take mean, definitely TV is having huge number, huge amount. So definitely you are spending so much. Maybe it is being telecasted for every 1 hour or every 2 hours. That's why the average is 147. Whereas on radio and newspaper, definitely the cost. The newspaper, if you are spending, it comes in somewhere in the corner of the back end page, somewhere there. So it is not up to the mark. Now, if you say mode, right, there's no one particular number which is being repeated most of the times. These are no NA value, but yes, these are the numbers which are repeating most of the times. And if you observe, there is a variation here, and the variation goes like this. A TV, you have so much of variation, with so much. You have to remember one point. When we are discussing about the variance factor, remember a point that okay. Okay, then what is happening here is when we try to find this part, you should be focused on one thing that you should have good variation. Okay, if there is no variation, the information content is very less. So more the variance, more the information, better for prediction. That is the stake we have here. So 7370 is the variance what you have. Then because it is a continuous data, you have to check for the skewness also. Right? So TV, you are having a negative skew. Radio is a positive skew. The newspaper is also a positive. Okay? Sales not required because it is an output. and kurtosis, and you can get it here done. See here, totally newspaper to pura skew hai. Maybe there are outliers are there here, right? A kind of, you can say that there's a very huge tail. That will result, because we know that the primary purpose of histogram is only giving you whether it is normally distributed or not, but it will give you a glimpse of outliers, right? So yeah, see here newspaper, because of this skewness what you're talking here, you got the two outliers, but here we don't see outliers and we don't have long tails also here. So to check whether we have the single go, I got this plot, all the plots, right? The one where it is a linear and you're having a maximum data points falling on the line, and we cannot say that it is totally normal, but yes, it's a kind of few, at least few data points are falling rather than the other three are totally sleeping. They are not linear only, right? They are not linear only. So here things like, if at all you want to do any typecasting, if it is required, here it is continuous data, it is good for our linear regression. We need not much worry about typecasting here. But what is happening here? It is duplicated, the data got duplicated here, right? And if you have null values, you want to sum up them, but it's lucky that we don't have null values and we did not get any duplicates also here. Okay, now the most important point of regression model building is that you need to find the correlation coefficient. How do you find the correlation coefficient here? One thing is that you can write np dot correlation coefficient x comma y, all the inputs. Here we have advanced visualizations available for us in heat map. Okay, SNS dot heat map, where it is a data dot correlation. If you just make it into data dot correlation, which is nothing but 1 1 1 1, that is a middle diagonal element 0.055, 0.055, right? Which is out of all this, right? If you observe, there is a very good correlation between these two, 0.9. Others, though you do an ad on newspaper, though you do an ad on radio, there is not much interesting increase in the sales happened. Okay? Not much interesting things happen here. So what is that we are interested in now? That can be also done here directly. This is the value. Okay, what is the interpretation here? TV with sales. TV with sales. So using this data set, the relationship between TV advertising and sales could be a better option for understanding how you can improve the number of sales. And it seems like more number of people are there who are watching ads on television, because they cannot, they don't have an option of the skip ad, right? Newspaper, so they can ignore, they can just remove that, right? So we can build our using a kind of feature engineering we are doing. We got this. So our equation would be like the equation what I wrote. Mx plus c, y is equal to m, I don't know. X is my TV with my intercept. This is my equation. There's one more plot here, which is called as a pair plot. Okay, there is a relationship here with a pair plot. This is a kind of plot where it is trying to find out the relationship, right? Instead of like same like heat map, it is giving in the form of a scatter plot. So 0.55, 0.55, right? With respect to hue, what it is effect. Now, how it is happening. So if you observe, this is very, very less, this is very, very less, but yes, TV is something which is very, very good with respect to this, the sales. Right? Most of the points are darker, right? They are very, very dark, means 25 sales happened, very, very light is the 5 sales happened, right? So now what you should do, you will go and build the model. So I won't want to delete those other two, newspaper and radio. We will build the model, sales tilde TV plus newspaper plus radio, which is equal to data, whatever data I have, and I fitted it. So the indication is this is the one what we have written. Okay, what we will do now? This is nothing but OLS regression results. This is the output summary we got. Our interest here is your R square value. Even before the R square, you have this input. These are the coefficients you got. So what is this interpretation now? It is y is equal to 4.625 plus 0.05 into TV data plus 0.170 into radio. This is the equation. And to our surprise, if you see p value of newspaper here, if you write hypothesis testing for this, for all beta 1, beta 2, beta 3, right? H0 is equal to beta 1 is equal to 0, beta 1 not equal to 0, you check with the probability value. What is the probability value? Probability value is nothing but you will, if the p value is greater than 0.05, then p high, you have to accept H naught. So this value should be 0 and it is very, very negligible. Newspaper is very, very negligible. It is no way important with our sales. But other values, yes, p values are very, very, very low. So p low, null should go. Null should go, right? And you have to accept these values, beta naught, beta 1 values. This is how the equation comes. So if I write this, let me take one value return. Okay, to know what is the sale, right? 230, 37.8, 69.2. Okay, these are my inputs. This is our output. Okay, it is nothing but 4.6 plus 230 into this value 0.05 plus 37.8 into newspaper 0. Plus radio. This is your actual value. This is your predicted value. But y minus y hat is equal to actual value minus predicted value, which is the error count. This is the first thing you have to check. And the second thing you have to check is your F statistic p value. Okay, F statistic p value. What is this F statistic p value? That overall, you are checking the p value for individual beta naughts, betas. But F statistic will give you a p value which is an overall p value. Okay, which is an overall p value. So that is also happens to be very, very low. It is nothing but 8.13 into 10 to the power of minus 99. Right? It means that it's very, very low. So yes, you can move forward with the model. And the second interpretation here is your R squared value. This R squared value. R squared value is nothing but you call it as the coefficient of determination. Okay, it is coefficient of determination. But if you are having 0.93, it means that for 100 data points, you are getting 0.9. It means 90 data points are correctly predicted. That is the interpretation. Higher the R square, better the model. The R what I explained and this R, they are different. That is R. This is R square. This range is from 0 to 100. It cannot be negative. Better the R square, better the model building. Higher the R square, better the model. So here it happens to be very, very good, 0.903. But only thing which is the flip side of our model is our p-value of newspaper is not up to the mark. You have to put an I because the p-value is high. You cannot take this value and go to prediction. That is it. Why the p-value is very, very high for the newspaper. If you start digging into that, we will understand few other things. Which one should you have to take a call and do that. So here there are few plots which is called as statistically. If you want to analyze it in a better way, you have an influential plot. That influential plot will give you, it will calculate studentized residuals, and it is going to give us which is less influential, which input is giving you like data point. Instead of input, I should say the data point. Maybe because of that data point, that weird pattern in your data, you are getting this plot, okay, is showing you 16, and because of that your newspaper is insignificant, right? So I'm dropping 16. Okay, I dropped the 16, and also I am taking a call that anyway newspaper is not having very, very good correlation between that and sales. So what will I do is I will just delete that also, and I pick a model which is nothing but this one, which is sales tilde TV plus radio. Two things led me to delete those two columns. It's just like a trial and error method we are doing. This trial and error method will help you to do this. Okay, so we have deleted that and we have deleted this. Okay, this is one thing. Now the point is we have to check for so many other values. There is no much difference here in R square value, but our main focus is on p value. So p values are low, null should go with accept coefficient values. Accept coefficient values. Intercept TV radio. P values are same. So what will be your equation now? Y hat is equal to 4.625 less 0.05 into TV plus 0.1 into radio. At least people are listening via radio and they're trying to purchase, they're giving a try for the product. Rather than newspaper, that is the interpretation here. That is a final model I do. I take this equation, I take the data which is available here on the top. In this data, TV and radio 230, 37, 37.8, I substitute here, I get the Y hat. Right? That is nothing but my predictions. These are my predictions. Okay, so now there are certain things which we need to focus. If you are, see, what is the error now? You have your final model built. In that you are getting something called as receipts. Receipts are nothing but you call them as errors. Receipts are nothing but errors. So what you should do, these receipts, you take them, okay, and you're doing a QQ plot. So QQ plot is that when you are building a regression model, there are certain assumptions which you have to focus. That is with respect to errors. What is that? Your error should be normally distributed. Your errors should be normally distributed. And what is the next thing you are checking here? Normally distributed. Errors should not have any relationship. They should be independent. They should be identically distributed. Right? They should be identically distributed. Okay, and errors should have, some of the errors should be least. Okay, some of the errors should be least, and there should be equal variance. If you observe, we did a scatter plot. Yeah, see here, errors are normally distributed, right? And if you observe here, there's a plot which is called as a recid plot. Okay, there's a plot which is called as a recid plot, and this plot will give us information about all this. So x is equal to pred, y is equal to data dot sales. See here, this is a line what you are getting, and all the data points are scattered here and there equally. It means that there is no heteroscedasticity problem. Suppose the scatter is something like this. Okay, it means that you are entering into a hetero problem. Equal variance means the line you are getting, the scatter, the data point should fall in this range only. If your data points are moving here and there, right? If the data points are falling here and there like this, and you got a straight line here, okay? We got a straight line here. What is that we can do? This is nothing but lot of variance is there. This is your best fit line, and your data got scattered like a V shape. So this is very much worse situation. Your model is predicting differently for different what you say people. So if I come, your model is giving you less error, right? And if I use television for one ad, it is giving me less error. For another ad, what I have telecast on television, it is giving me more error. Consistency is not there in the errors. If I use this for every data point, it is behaving weirdly. So to overcome that problem, that is called as heteroscedasticity problem, there is a concept called as you have to apply transformations to make your data with equal variance. You should do transformations. Okay. The good thing is that yes, we got a line, These are identically distributed. They are not dependent. You don't see any pattern here. They are irregular. Right? So this is the conclusion. This is a final model. Now what we will do is we will go and split the model, train and test split. And you have to check whether the model is overfitting or not. If the model will overfit, again, like KNN and decision tree, we need to use some regularization techniques to solve them. Okay, now from sklearn.model_selection, we are importing train test split. Okay, the split is 80-20 ratio here. This is my final model, but the data here I'm taking is the train data. So 20% of the data would come here in train and test, and 80% would come in the train data. Okay, I'm building the model. So it is statsmodels.formula.api, smf.ols, sales tilde TV plus radio, which is equal to this. Okay, so model_train.predict here, model_train.predict. What is that you should pass? I should pass my test data. Should pass the test data. Model_train.predict is my test data. So these are my random numbers. See here, randomly I got different test data. Here I got this. These are the sales prediction. Only the relationship is taken with TV and radio. Okay. 20% of the data. Now if I predict the same thing on my train data only. Okay. I predict that on my train data. These are my. So I'm just cross-checking it whether if I have been given a data and I'm also being asked questions, whether that model is working well on the training data or not. It is called as a training data. Okay. Now what is that we do here? We need to know the receipts, nothing but the errors. Errors are nothing but test_print minus data_test dot sales. Okay, this is my y hat. This is my y value. Y hat minus y will give me the error, and these are the errors. So 80-20 ratio we have. These are the errors for train data. These are the errors for test data and train. So here you have to remember one point where we have seen confusion matrix as the evaluation metric for classification. For regression, okay, for regression we are taking root mean square error. So what is this root mean square error? Suppose I have a model like this. Okay, this is my actual value and I write the predicted value. If I do subtraction of this, -1, -1, -1, -2. 100 minus 101, -1, -1, -1. Let's make it 101. Okay, some values are plus, some values are minus. Okay, everything gets, if this is there, it gets nullified and actual plus predicted value, this is the error 0. But given the error is 0, right? So what will happen here? Though there is some mismatch in the actual and predicted values, you are getting the error as 0. So that is not able to capture the exact errors. If you are just doing sum of the error, if the summation, if sum is only 0, what the average? So what people thought that we square the error. Okay, it is squared error. So what is that squared error means? Here is if we are taking into consideration some amount. Now it is the amount, the budget allocated in the number of product you are getting. The sales means sales, product got sold out, and that is also an amount. This is also amount. Amount square. If it is in dollars, you get the dollars square. You get the dollars square. Okay, so you have, if you take mean of it and you do square of it, it is mean square error. Your error also is a dollars square. So what will you do? You have to do square root of it to get back the units. So that's the reason for regression based algorithms. So this is a test receipt, this is a test receipt. Square them, take the average, square root of it, which is a RMSE. So if you check, the RMSE value is very, very small data set. This is 1.49 and this is 1.68. So it means that your model is a right fit. Both are nearly equal. It is a right fit. So the point you have to focus as a part of linear regression, you call them as line assumptions. So for this data set, I have just deleted newspaper just like that, but you should not delete any data point just like that. We have to run it putting newspaper also. So what you can do is, the thing is, if we don't want to delete it, you have to put newspaper here. Capital N, small p. Fill the model. Right? See here, it is very, very high. P value is very, very high. Right? To make, if such a situation comes also, we will have to do some kind of transformations and make that P value also significant. Still it is not happening. Then there are a set of things which you have to know. These are nothing but added variable plots, or you have to see partial regression plots. Both mean the same. We are trying to find the effect of newspaper, right? But this is not a multicollinearity problem, right? So that's why we took a call, because if you see, none of the inputs are also having very, very good correlation. Radio is an input. This is also newspaper is an input. Right? Radio. So that problem is not there. That's why we did not get into much of the things, and we did not deep dive like we have various inflation factor to find out the collinearity. There is no problem of collinearity. The only problem here is your newspaper P value is insignificant. Okay, so what you have to do is, if at all you want to apply some log of newspaper, apply some kind of transformations, and you can check. Sometimes here we did not observe much difference here in your R square value, because already it is 0.90, right? It's already 0.9, but yes, sometimes we get to see that that R square value also would increase. This is R square value. Okay, if you delete and if you add, suppose now you added one more YouTube or something, so you have added some e-commerce like YouTube, you have added, you are doing an ad on YouTube. Okay, this is a budget allocated. If you're adding this YouTube, your R square value, the other input data will increase. Okay, your R square value will increase. But really, YouTube is also helping us to increase the sales of that particular product ad campaign. How do you know that? Just like that, you have taken some data, client has given us, we'll work with that. That way it is not going to work. So we have to check the corresponding adjusted R square value, because the added input is having good effect on the sales or not. Why? We are checking via this. If both these are going hand in hand, right, that YouTube is important only, Facebook is important only, Insta is important only, like that means important input for prediction of Y. Means the sale of a product is having some impact. So if you do an ad or via YouTube, the sales are increasing. Because nowadays people are spending more time on these platforms only. But what it would drive model overfits. The regularization technique we are using here is lasso and ridge regression. It is nothing but lasso and ridge regression technique which will solve the overfitting, where it is going to penalize the effect of, effect, and now we have by default deleted newspaper, right? So it will adjust the coefficients in such a way that the model will not overfit. But for our the understanding here, we did not get overfitting problem, right? So because of that reason, we need not worry much about the overfitting problem. It's a right fit. Okay, so that's it. This is a linear regression model building. Why being numeric? If at all you have multiple inputs here, we will say that we will go for multiple linear regression. All are continuous data, so much pre-processing is not required. Okay, much pre-processing is not required here for our understanding. Okay, so thank you all for joining in this regression model building. Thank you.